Okay, so this is a very fast addition, if you like, to the organic redox that you have, and that is that we thought we needed to just touch base again on some of the physical chemistry, really most of which you study at A-level. So I have a sort of intrinsic issue here responding to feedback. I am not going to dwell on what you did at A-level. I've uploaded some movies covering oxidation numbers, balancing redox equations and galvanic cells that I know all boards have almost to excruciating details in their A-level syllabus, and I'm just going to start straight off here, right? I do suggest that if you don't remember this, that you go back and either look at your A-level books or the pages in the textbook or the movies I've uploaded, but this is the material that we're going to be focusing on. Anyway, you of course remember from A-level, from stuff last semester, from stuff this semester, the definition of spontaneous and non-spontaneous, and of course the way in which delta G 0 less than 0 for spontaneous, delta G 0, and I know I shouldn't be using 0, greater than 0, a spontaneous reaction, and of course this relates to the equilibrium constant. Greater than 1 is spontaneous, less than 1 non-spontaneous when you're starting from standard state. You also, at A-level, talked about E0, right? So this is the EMF for an electrochemical reaction, for a redox reaction. And should this be greater than 0, then it's spontaneous, less than 0, non-spontaneous. Okay, so this is actually stuff from A-level. Now, of course, in A-level and our materials here, we know there is a relationship between delta G0 and K, as there should be, because you can see this definitive relationship here. Well, of course, it will not have escaped your attention, I hope, that there must be some kind of connection, therefore, between delta G0 and E0, and thus between K, the equilibrium constant for that redox reaction, and its standard EMF. So that's really what we're going to talk about in this movie, the relationship between delta G and E, and the relationship between K and E. So back to the idea of potential. If you watched my movie, you will see that I related our potential electrochemically to potential energy. Okay, we have a little man standing at the top of the cliff. He has potential energy mgh. And of course, if he goes off, that energy turns into a half mv squared. Same idea for our electrochemical. We now have a height of the potential E. So we have the left-hand side of an equilibrium at the top, the right-hand side at the bottom, and this is the electrical potential associated with that reaction. And the energy that we will get from that is delta G. Okay, so in other words, mgh, excuse me, associated with the cliff height and the little man, is the same concept, at least, as the relationship between delta G and that cell potential, or the potential for the half reaction or the whole reaction. Okay. Now let's construct these equations together, shall we? Potential energy for our little man, H, cliff height, and for our reaction, E, the potential. You then have mass for the little man, right? I'm sorry, should I say little person? I need to be politically correct, little person. Okay, and mass of little person, the amount of the substance that is undergoing that change, if you like, when it changes, that is at the top of that cliff height. Well, what's the equivalent for our electrochemical reaction? Well, it's the electrons that are going through this, and of course we always talk about it in terms of moles. So it's the moles of electrons, little n, which relates to the moles of electrons in the balanced equation that you write out, that you balance according to what you did at A-level, what's there in reviews. Now what's G? Well, G is just a little constant. Okay, first of all, it has a physical meaning, but it's also there to balance units. So let's look at the units first. The potential energy units are joules. Okay, and joules you can rewrite as kilograms per meter squared, second squared. Well, we've got mass is kilograms and the H is in meters, so that's pretty good. We got rid of a couple of those, so that means that G has to be in meters per second squared right here. In other words, it's an acceleration. Here, of course, we know it's the acceleration according to gravity, which has the value of 9.81. Okay, let's balance our units over here. Again, the units of delta G will be joules. Units of moles of electrons are moles of electrons. Units of E, the potential, are volts. So therefore, what must our constant have as its units? Joules per moles of electron volt. In other words, what is the energy associated with taking a mole of electrons and moving it through 1 volt? And the value of that is 96,485. When you take a mole of electrons, you move it through 1 volt, that is an energy of 96,485. You either have to put that in to force it up, or you get it out when you let it come down this potential. And that is a Faraday F, which we stick in there. And yes, that is the same Faraday that you encountered when you were doing electrolysis. And the very last slide of this movie is just showing you the equivalence of those things. Anyway, there's our nice little equation, right? Potential energy is equal to mgh. Energy of our little electrochemical reaction when a mole of electrons goes from here down to here, I hope there wasn't a nasty gap there, is delta G equals minus NFE, or if we do it in terms of standard state, delta G standard state, excuse me, but I don't have that fancy little symbol to hand here at home, is minus moles of electrons, N, that's the number of moles of electrons associated with the balanced redox equation, times F, 96,485 joules per mole of electrons volts, times that potential. Okay, so that's our relationship between delta G0 and E0. Now I said we'd like to have a relationship between delta G0 and K, so let's look at that, shall we? Delta G0 is minus NFE0, and of course delta G0 is minus RT times the natural log of K, or thus, substituting that in, we get minus NFE0 is minus RT times the natural log of K, or E0 is RT over NF times the natural log of K. We can go a little bit further than that if we want to. This all deals, of course, with standard state. In other words, where you remember the reaction line I introduced you to last semester, you start off at standard state, Q equals 1. If the reaction spontaneously goes to the right, well then K obviously was greater than 1, delta G0 is negative, and E0 would be positive. Conversely, of course, if we're going spontaneously to the left, that means that K is less than 1. Delta G0 would be a positive number, all right? Not sort of saying it's non-spontaneous period, but saying it's non-spontaneous to the right because it's spontaneous to the left. And of course, if we start there and we go to the left, E0 would be a negative as well, okay? Now let's move from being at standard state. So instead of delta G0, we got delta G. Instead of E0, we got E. And you might remember the relationship here, that again we derived last semester, that when we are not at standard state, we talk about delta G, we can relate that to the Q where we actually are, and the delta G0, that's starting off at the standard state of Q equals 1. Okay, now let's substitute in there, shall we? Instead of delta G, we have minus NFE. Instead of delta G0, we have minus NFE0. We get this rather pretty looking thing here, which we can divide all the way through by minus NF, and we get the so-called Nernst equation. E, in other words, the potential where we are, equals the standard potential minus RT over NF times the natural log of Q. Back in the days when this was done in A-level, and I'm told and I understand that almost all the boards do not do the Nernst equation now, a lot of times you'd see it as log Q, right? Other times you'd see them trying to put together R and the T and the F in one big constant, saying, well, let's see what happens at 25 degrees Celsius or 298 Kelvin. And you get a little number here that was 0.0257 if you're using natural log, or 0.06 if you're using log to the base 10. So you'll sometimes see the Nernst equation written that way. I would recommend that you remember it like this, okay? Anyway, there we have essentially the new concepts. So I've only gone for 9 minutes. Let's do a couple of examples. So this is an old equation that I have, an old question that I had for my old students back in the States. Value V0 for the cell, blah, 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 1.59 volts. What is delta G0 for this reaction at 25 degrees Celsius? So the first thing you have to do is unpack, to use Andrew's favorite expression. Actually, I don't think that's his favorite expression, but it's an expression he uses an awful lot. Unpack this cell notation, okay? And we see that the oxidation is going from chromium to chromium 3+. The reduction is going from Hg2 2+ to Hg, okay? So we can write that actually in the proper equation words, the oxidation chromium going to chromium 3+, Hg2 2+ going to Hg. We can throw in the balanced version. If we've got 2 Hgs, we need 2 Hgs there. And then we got to put in the electrons, going from chromium 0 to 3 plus, obviously change of 3 electrons. Here 2 plus down to 0, change in 2 electrons. This is actually an interesting little cation. It's mercury 1, otherwise known as the Mercurous Cation, which doesn't occur as Hg plus, it occurs as the diatomic dication Hg2 2 plus. But anyway, we're not dealing with mercury chemistry, we're dealing with electrochemistry here. So you've got 3 electrons in one, 2 electrons in the other. That tells us that the n we're going to use is the least common multiple of 2 and 3, which is 6. So delta G0 is what we want, minus NFE0. Throw that in, n is 6, F 96,485. I tell you that the potential 1.59 volts, and we get delta G0 minus 920,610, or about minus 921 kilojoules. Piece of cake, huh? Bit more fun. Going to, using the Nernst equation, calculate the value of E. Notice that I have not dealing with E0, I'm just dealing with E. This question actually reads tables, which you could get, right, the half equations associated with Ag plus going to Ag, the reduction potential plus 0.8, going from copper 2 plus to copper, plus 0.34 volts. Okay, both of these given as reduction potentials, which hopefully is how you remember they are given. Let's look at the equation we actually are dealing with, the reaction we're dealing with. The oxidation is copper to copper 2 plus. The reduction silver plus going to silver. I put in the electrons easily because you can see those. Now the reduction is easy, that's plus 0.8. However, the oxidation, we're now flipping this whole equation, so we've got to change the sign, so it becomes minus 0.34 volts. Thus, E of cell is 0.46. If you don't remember how to get that, you can either go back to your A levels. I suspect they treated it differently from I did. I see absolutely no reason in the way they do things in that the oxidation potential for copper is minus 0.34 because the reduction potential for copper 2 plus going to copper is plus 0.34. Anyway, E0 cell is 0.46. And n is, of course, 2. Least common multiple of 2 and 1 is 2. Now, there is the overall equation. Copper plus 2 Ag plus goes to 2 Ag plus copper 2 plus. From that, we can get Q. Okay, we're not at standard state, so we need to figure out what Q is. Okay, and this copper is a solid, the silver is a solid, so those do not feature in Q. And we are told these concentrations, copper 2 plus, concentration of 1, silver plus, concentration 0.001, so we can calculate Q is 1,000,000, 1 times 10 to the 6. Now we've got all those, we can plug them in to our beautiful, gorgeous Nernst equation. There it is, slamming in. E, right, the potential at non-standard conditions is equal to E0, the potential at standard conditions, which we can get by a consideration of the standard reduction potentials, is 0.46. Is R, 8.314 joules per mole Kelvin, times temperature, always assume 298 if not otherwise told. N, number of moles of electrons associated with the associated equation, is 2F 96,485 times the natural log of 1,000,000. This whole thing boils down to 0.18, and so we have that the voltage here is 0.28 volts. Now you can actually think about that in terms of the reaction line. Okay, I should have actually put this in a slide, but bear with me. Reaction line going like that. Standard state, we start here at Q equals 1. We're going to go over here, right, to equilibrium, and the potential associated with that is 0.46 volts. However, we're not starting at Q as 1, we're starting at Q as 1,000,000, so we're going to be closer to that voltage, so therefore the voltage to go from where we are, 1,000,000, is going to be smaller than the voltage from starting at Q equals 1. So therefore 0.28 compared to 0.46, and that difference associated with Q being 1,000,000 is 0.18 volts. Do some of these, of course, in class. Go through them a bit more slowly, but hopefully you'll have a look at these and be able to figure it out. Promised you we'd look at the units of the Faraday. We've just talked about a Faraday, 96,485, is the number of joules associated with moving a mole of electrons to a potential of a volt. Back in A-level, you dealt with a Faraday was coulombs per mole of electrons, the charge per mole of electrons. Well, the only thing that they've got in common is moles of electrons, but somehow they have to be equal. So how are joules over volts equal to coulombs? Well, stay the joules over volts all on their own for now, but remember that coulombs is equal to amps times time in seconds. Okay, rearranging those a little bit to get joules over seconds on the left hand side, amps times volts on the right hand side. And those of you who remember your physics will remember that joules per second is actually a measure of power, which is measured in watts, and amps times volts is the power of the electrical flow, which is also in watts. So yes, indeed, joules over mole of electron volts is equal to coulombs over moles of electrons.